Most of you will know now how important therapeutic oligonucleotide, especially in the last few years. So therapeutic oligonucleotides are there for few decades, but just in the last 5 years, we have kind of 15 therapeutic oligonucleotide out of 16 in total, which is approved from the FDA. And in fact, this happened mainly because we can find one now ligand which can deliver it, although it is only for the liver, but it just made more people kind of think that this might be the solution for many diseases which we can't cure now. Of course, the small molecules are there for long times. They can, cure many diseases, but sometimes they are not specific, and sometimes we can't have even target for many diseases. So here a few examples of diseases which you can think about when you think about therapeutic oligonucleotides. So incurable cancers, which so far there is no specific molecules to just specifically kill the cancer. And also, it is sometimes complicated. So the cancer itself might be component, like many components inside the cancer itself. So you might have specific for one protein, but there is more than one protein involved. Also, infection disease, therapeutic oligonucleotide can be used for that, and inherited diseases. Most of the oligonucleotides now are approved for rare diseases. And because it always, the pharma were not really interested in therapeutic oligonucleotide because, of course, the approval is much harder because you cannot purify it, especially for M-1 in oligonucleotide. So to get it approved, it was really tough for them. So most pharma or big pharma were more interested in small molecule because it is very easy to get. You can screen, you get identify it, test it, and it is easy to be approved because it is easier as well to test the toxicity. But because recently, after the biology kind in the last few years, in fact, evolved a lot, and now we know that it is not only the proteins which reduce the disease. It is mainly there is non-coding DNA and non-coding RNA, which is responsible about a lot of the disease. Having known that, everyone, especially pharma, started to think about we have to move to oligonucleotide and start to face it and solve the problem which is in this field. So for therapeutic antisense, which I'll focus on today, we all know that you have the DNA transcribed to the RNA and you make the protein. And this protein somehow, one way or the other, will be responsible about the disease. So you can have some diseases which you have more of the protein, or you can have diseases which you have less of this protein. You can have diseases which the protein is there, but it is faulty. And maybe if you just reduce the size of the RNA and then you make, although it is shorter or smaller protein, but it is more function. So if you focus on the RNA and not the protein, for any disease you cannot cure the protein or you cannot produce, then the way to destroy the RNA, so you stop making the protein, will be via 3 ways in the anti-way. So either you block the messenger RNA, then when it goes to the ribosome, then it will block it and not transcribe. Sorry, not translate. Or you can have the antisense oligo hybridizing to this, and it has specific properties, a specific sequence as specific properties. Then you can introduce RNase H and it can destroy the messenger RNA. Or you can block this and have the protein made from only this part. So you will skip this part, and in the exon skipping, you skip this and you make the protein from, say, 2/3 of the protein will be there, but it is function. When it was, say, the full protein, it will aggregate, and then you have, especially in the muscle disease, you will have aggregation, accumulation of it, and it causes the muscle disease. But if you have it reduced, it will not be 100% function, of course, but at least will do if you can think about it, just half of the job better than no job at all. So you will ask yourself the question, it is easier to screen small molecule to protein, it is easier to cure. As I said just earlier, some proteins, you cannot get small molecule specific to it. Good example for it will be cancer. We all will know someone who died not from the cancer, but maybe died from curing the cancer, which means that from the chemotherapy itself, the people can suffer. And instead of having just like, of course, there are some some cancer medicines there which will cure, but I'm saying, and the majority of chemotherapy now are really going everywhere because it is small molecule and it will go everywhere. So, and in addition to that, there is also, as I said, most of the RNA are not coding for protein. Most of them are non-coding RNA. And so far, not the function of all of them are known, but mostly people in biology now trying to solve this problem to know what kind of messenger RNA, which is non-coding RNA, responsible about which disease and so forth. So if we can target this RNA, of course, we don't need small molecule to the protein because there is no protein. It is just non-coding RNA. So here will come the importance of having a specific sequence to go and target the RNA. So the good thing, of course, about DNA or RNA, if you have it as a medicine, that is a specific sequence. So it will not go anywhere if, of course, if you choose it correct, it will not go anywhere apart from the messenger RNA you are targeting. So we have here, this is the sequence. This will be the ligand. So you can find many ways of making this. So you can have your specific sequence. You can also, the good thing about messenger RNA, it is very long. Then you can choose the best one which will bind best. You can choose the best modification which improves the binding affinity. So you have a lot of factors you can control. The small molecule, it is kind of try and error. Of course, you can see exactly the bucket of the protein, design your molecule exactly. But here you have more flexibility. You can also direct your molecule instead of the small molecule, which will go anywhere because it's just easy to deliver. Now you can control the delivery. You can have ligand, which you can now join to your sequence and direct it to only the cancer cell or only to the cell which you want to do, to the brain. So by having ligand, which is a big problem now, of course, we didn't solve this yet. The whole community is struggling to solve the delivery, but this is the way to go in future. This is some of all the medicine which are there. So as I said, it started at 1978, and now in 2021, we have mostly 15, I can't remember the number exactly, 15 or 16 so far. And you can see most of them just from 2016, 2021. So of course, once big pharma starts to be interested in the field, this will increase the interest on it. Because of course, we were in this field many, many years ago, but we stopped because the interest is not there. No one is listening that we need this, we need the delivery, we need to solve this problem. But now all pharma are there supporting the community. I think we will soon, instead of having just 16, we will have much, much more. So the rate is really high now. So a few years ago, we started to think, shall we go back to this area now? Shall we go back to the therapeutic oligonucleotide? So we needed to think, what can we do? As a chemist, you can, of course, most of biologists will just buy the oligonucleotide with the modification which is available. So they have like limitation of what they can try. We are lucky as chemists because you can do what you want. You can imagine anything. So what we thought that big problem in the DNA or RNA will be the charge. So it is negative charge. So it can't easily go to via the cell membrane. So we thought about neutral backbones. We have one backbone in our lab already, we were working on it, and we thought, can we use this one? This is just done by click chemistry from alkyne and azide. So it is 5' azide and 3' alkyne. And of course, the neutral backbone will have few advantages. So nuclease stability, we think that it should be stable to nuclease. Target specificity, this will come from, of course, the sequence, but also will come from the affinity. So the affinity is something which we thought we should work at. And toxicity, this is something we have to try. And we are hoping that this will deliver easier via the cell membrane. I'll give a bit of introduction to this backbone. Why did we choose this backbone? And what did we do in the lab? So before we use this in the therapeutic oligo, we have a few projects running. So I'll give just a bit of introduction. So this is long backbone, which we used click chemistry for just nanotechnology application. So we didn't need to think about the length of the linker at the time. Then we thought to use this click chemistry for biocompatibility. So we thought, can we make modified gene using click chemistry? So the idea was, if we can replace the phosphate and we make few long oligos to produce one long oligonucleotide with few of these triazoles in the middle. So if we have, say, 500 mer of 5 oligos, and we introduce the alkyne and the azide modification at each end of the oligo, instead of using ligases, so we just have splints and we make this piece of long DNA. Because if you know about solid phase chemistry, in solid phase, you cannot really make more than, say, 200 mer DNA. For RNA, it is even worse. So we used it to make the whole gene, and we used it to make very long RNA as well. We used it to make library of CRISPR RNA. So you make one of the strands in large scale, and then you build library. So instead of making library of 100 mer, and biologists use a way to do it, but it is a bit complicated. So we thought, if we make short RNA, and the long one will be in large scale, and we make one library just in one test tube, and we can make any number of RNA in the same test tube. So by choosing this backbone, which was, of course, biocompatible, we made the library and we proved that it is functional. We tested this as well in bacteria, so we know that this backbone is really biocompatible. So, but we know one disadvantage of this backbone, which was the thermal stability. And why do we need the thermal stability to be high? Because we want it to be specific, so we want the affinity to be high. So we thought about few modifications which we can introduce to this backbone to improve the affinity for therapeutic. For gene synthesis and for RNA, it really doesn't matter, because it was tiny bit lower TM, but it doesn't matter for any application we've done so far. But for therapeutic, you will have maybe 4 or 6 of this modification in short oligonucleotide. Then the thermal stability now will be more important than when you have 3 or 4 every like few hundred mer DNA, normal DNA. So we thought about LNA, because LNA was already there and being used in therapeutic oligonucleotide. So we thought that we can put it around the triazole, at the 5' end of the triazole and at the 3' end of the triazole. And we did it, we did the synthesis, and we incorporated it in the 3' end of the triazole, 5' end of the triazole, or at both. So we did this via 2 approaches, because it is short oligonucleotide, so you can do it by ligation, the same way we did it for the gene, but of course for the gene it was very long oligonucleotide, but we thought it might be a way of doing the short oligonucleotide, easier way than just to test the thermal stability before we make all the monomers. So we did short oligonucleotide with alkyne, short oligonucleotide with the azide, we ligated them, and we have oligonucleotide with 4 of these triazole and LNA in both directions. So with the LNA, with the triazole in the middle, we have like reached, like if you add this 4 times, you have increasement in TM, which is few degrees. But this is coming from, if you have the triazole alone, it will be lower TM than the native phosphate. So now we are having higher TM, but also we have more neutral backbone. So we were hoping that this will help in thermal stability, will help in also enzymatic stability, but the big hope, of course, to help in delivery. So this is the TM. You go from minus to plus, not huge. Of course, it enhanced mismatch, which you need really to think about mismatch, because this what will affect your off target, because you want it to be specific there. So even if there is one nucleoside different in part of the gene, you don't want to go there and affect it. And enzymatic stability, we also proved that it is higher enzymatic stability. As you can see here, the oligonucleotide, which has got the LNA triazole, is more stable than the oligonucleotide, which unmodified or has got LNA alone. So the LNA alone, which will have the phosphate still, will not be as stable as if you have neutral backbone and the LNA in the same time. And the oligo was stable for a few hours. So we tested the thermal stability. It was higher, but not as much as we were hoping, because we started with lower TM, which is the triazole, and then we went, so the LNA compensated that, but it didn't really increase it that much. We thought about the amide after that, so because we had the amide as well for the same reason, we were using it for gene synthesis. It is harder to make than the triazole, so that's why we were keep like delaying it. But in the end, we thought that if we want to go to therapeutic oligo, we really need to use the amide. So we choosing it because, of course, it will overcome. This is some of what commercially available phosphorothioate, 2'-omesyl, 2'-OMe, fluoro. So the advantage of the LNA and the amide, it can reduce the toxicity, which might caused by the phosphorothioate, because we all know that phosphorothioate will give 2 isomers, and each one will give you 2. And if you have 20, so you have 2 to the power of 20, then it is huge number of isomers for each molecule of oligonucleotide you will make. But the amide, at least you will reduce. You will not have it all amide. So if you have 6 amide, then you reduce the number of molecules you have inside each oligonucleotide. So how did we do that? So we prepared 2 monomers, one with acid molecule at the 3' end, and one of with amine at the 5' end. So we start the oligosynthesis, and we add first, of course, you add all the sequence, which will be normal phosphothioate, and then you add your amine, MMT, then you cleave it, then you do the normal cycle, and then you add your acid with the DMT. So you add this manually. I mean, you can imagine in future, if this worked well, then we can automate it. You can just use machine, which will do oligonucleotide synthesis and amide synthesis in the same time, or just go from the DNA synthesizer to the amide coupling or peptide machine. Sorry. So you add your acid, you do the amide coupling, and then you remove the DMT, add the normal monomer, and so on. So each cycle will be between just adding the normal monomer as amine, and then by amide coupling, add your acid, and then carry on the oligosynthesis. So, so by the end, you will have your oligo with whatever number you decide to have as a neutral backbone, 2 or 4 or 6 or whatever. It depends on, of course, the sequence. And this is the mass spec of the crude oligonucleotide after making it. This is 18 mer, and this is the crude oligo, and this is, of course, the correct mass. So the synthesis was really, I mean, it needed some optimization, but in the end, it was really perfect for this number of modifications. We had normal amide. We had, again, we wanted to see if there is difference between the triazole and the amide or not. Forgot to mention that for the triazole, we found that the LNA has effect only if it was at the 3' end. So when we had the triazole backbone, when you have the LNA at the 3' end, it increased the TM. But when we had it at the 5' end, it didn't have any effect. That's why the combination of them were higher a bit, but mostly the effect coming from the 3'. And we thought that it's just because here you have phosphate, then it is blocking the phosphate. That is why it is reducing the flexibility and it is giving higher TM. In terms of the LNA, it was different. So we had effect from 3' end at the 5' ends. So we increased the TM from the LNA in both sides, from the 3' end at the 5' end. And of course, we increased the thermal stability higher when we have it in both 3' end and 5' ends. So this was improvement over the triazole. So the TM here, or the thermal stability here, is higher than what we got from the triazole. And here you can see that by having 1 LNA amide, 2 LNA amide, or 4 LNA amide, it was much more higher than the normal phosphorothioate backbone, or the phosphate as well. We tried to do shorter oligonucleotide to test. First of all, we wanted to know, is the B backbone going to change or not if you have 4 of the LNA? We did the crystal structure, but we included only 1 just for simplicity. And sorry. And as you can see, if you overlap them, you can hardly see any difference between the amide and the normal phosphate. And this is what we've seen as well when we did the gene sequencing. And we realized that the most close backbone, neutral backbone to the normal phosphate was the amide over the triazole as well. We did some very preliminary cell uptake, and we can see here that the toxicity is lower and the activity is higher as well. So we know from here that toxicity is lower. We know from here that activity is kind of 5 times activity that when we tested it in HeLa cells in luciferase assay. Although it is very preliminary results, but because it is what we expected, we think that it is promising for delivery. So we think that the activity is coming from the delivery, because when we delivered it using just normal alphyctamine, it was more or less the same as the normal phosphothioate. But when we nakedly delivered it without any transfixion agent, we've got these results. Of course, as I said, this is very preliminary results, but we are in the way to test it in different cell assays and test the toxicity in animals as well. This is just to summarize that we believe that if we can combine the phosphothioate and the neutral backbone, we can go through the cell membrane and the nucleus. And this is our hope anyway. I want just to thank the team who put this all this effort in it, especially Isabel, who drove the project for the amide. She really did a good job because it wasn't easy. The triazole is really, really easy to make, but the amide is not easy, and she was really dedicated to get this project going. I want also to thank other people who were in this study, especially Cam and Jack and all the people, I don't want to forget anyone, who helped in the crystallography. I want also to thank BBSRC and ATD for financial support. And thank you for your attention.